Okay, next talk by Senthil.
Thank you very much. It's been a great pleasure to be here. Is there a pointer? Great, thank you. It's been a pleasure to be here. I've learned a tremendous amount already in this conference, much, 100 times more efficient than Zoom talks. And it's been really, really stimulating for me, both to hear the talks and to chat with people during coffee breaks and so on. So the work that I'm going to talk about was done with several students and postdocs. Hee Zhang is one of the heroes of this collaboration. He's a former student of mine, soon going to join Johns Hopkins as faculty. So Dan Moore recently graduated from my group. He's now a postdoc at Cornell. And Jihuan Dong is a graduate student at MIT. And Cecile Repelin was a postdoc with us and now a faculty member in France. And delightful interactions with experimentalists in the field, Pablo Feng Bang at Berkeley and David Goldhaber-Gordon, and their army of wonderful students and postdocs. It's been really stimulating to be part of this community. So let me start by reminding maybe the students in the room about the conventional story of magnetism and insulators, going back to Phil Anderson. In an insulator, magnetism comes about first because of mode localization. So you have, say, one electron per site, and then the question is what happens to the spin of the electron. And the fate of the spin is understood by treating the electron hopping in perturbation theory around this mode insulating state. And we, and as Sanderson pointed out, at second order of this perturbation theory, you get the super exchange interaction, which tends to line things, neighboring spins up antiferromagnetically, right? And this is the standard story. It gives rise to antiferromagnetism as the most common form of magnetism in insulators. There is a mechanism to get ferromagnetism in an insulator, worked out by Goodenough and Kanamori and others in the 1960s. But it's rare, and it gives, even then it gives ferromagnetism, the ferromagnetism is very weak. So this is the standard story of magnetism insulators. So we can ask when this usual picture is legitimate, right? And your chemical potential in your solid is somewhere, and there are a set of bands that are at the chemical potential. That's what I'll call the active bands. And for this, one of the points of this talk is that this usual picture is legitimate so long these active bands near the chemical potential are topologically trivial. Okay, so the reason that's necessary is that it's only if they are topologically trivial can you define well-localized linear functions, which is what provides the foundation for writing down a tight binding model and a lattice description of the interacting system that we use to discuss the strong correlation limit and do perturbation theory in the hopping and so on. So if the active bands are topological, then we lose the one-year basis. And so then any correlation-driven insulator, the nature of magnetism and other such things in the insulator must be re-examined, okay? So as an example, the simplest topological band is a Chern band. So we can ask about correlation physics, say in a half-filled Chern band, right? The analog of what's strong correlation physics in an ordinary half-filled band, right? Now for a Chern band. So we'll have the usual competition between the Coulomb repulsion and bandwidth, but playing in the setting of a topological band, okay? So for weak interactions, we might expect that you just get a Fermi-liquid metal because you're half-filling a band. But for strong interactions, perhaps you will get a correlated insulator. And if you do get a correlated insulator, you can ask what the spin is doing, pose the same question as is done in usual mode insulators. And for intermediate interactions, perhaps we'll get all kinds of new states of magnetic matter that are specific to living in a topological band, right? Now, amazingly enough, so precisely this question turns out to be extremely relevant to many of the ongoing experiments currently in correlated moire graphene and correlated TMD heterostructures. Okay, so since that is the reason to pose these questions now rather than 10 years back, let me talk a little bit about flat bands in moire graphene. There are many routes to getting flat moire bands in graphene. So the classic route, the field has evolved so rapidly that I call this classic as twisted bilayer graphene. Take one layer of graphene, twist it relative to the other layer, and tune to a magic angle. But the community has explored all kinds of other structures. You take n layers of graphene, twist it relative to another n layers of graphene, and tune to a magic angle, and do twisted double bilayer, twisted monolayer bilayer. All kinds of experiments have been going on. A different route is to take n layers of graphene and align it with a boron nitride substrate. And there's a slight lattice mismatch between graphene and boron nitride that gives rise to a long period moire pattern. And that also leads to flat bands. And this is nicely demonstrated in ABC trilayer graphene on boron nitride by the group of Feng Wang at Berkeley. So the outline of the talk is that I'm going to start talking about the strong interaction limit for a half-filled Chern band, for these half-filled bands of moire systems. And I'll start with some review of some old work, meaning from a couple of years back, on spin valley ferromagnetism at these fillings and the prediction of an integer quantum anomalous Hall effect that came out of some work that he did when he was still a graduate student. And then that'll set the stage for the newer work. I'll talk about new states of quantum magnetism at intermediate interaction strength that might exist. And then finally, if there's time, I'll talk about the prediction of a fractional quantum anomalous Hall effect in these same systems when you dope away from integer fillings. So let me quickly review some of the features of the band structure of moire graphene pertinent to this talk. Now, there's a lot going on in moire, so I won't have time to discuss everything in moire. The first key feature is that apart from spin, there's a Valley degree of freedom in these systems. And the moire potential, what it does is to decouple the two valleys of the underlying graphene from each other, so that the valley really acts as another internal degree of freedom in describing the many-body system. And in many moire materials, we can isolate within each valley, we can isolate the valence band from the conduction band so that these do not intersect or touch each other. This is not true in twisted bilayer graphene, the classic system. Therefore, within each valley, the valence and conduction bands are connected by Dirac points. But in many other moire graphene systems, you can detach the valence and conduction bands from each other. So when can you detach them? And this is really a question of symmetry. In twisted bilayer graphene, the Dirac points within each valley are protected by a symmetry, a combination of C2 and time reversal. So that C2T symmetry, so long as it's there, you can't gap out the Dirac points. And if the symmetry is absent, then generically, there's no protection of the Dirac crossing, and you will get a gap between the valence and conduction bands. And this is seen very nicely, for instance, if you take twisted bilayer graphene and align it with the boron nitride substrate, the boron nitride breaks C2, and therefore you break C2T, and then at short neutrality, you develop a gap. Okay? Now, so early on, 3 years back, we realized that in a large number of these moire graphene systems, that the bands will be topological. And topological in a very simple way. The flat bands of the two valleys will have non-zero Chern number, but since the two valleys are related by time reversal, they'll have equal and opposite Chern number, C. And you can calculate this for a variety of systems. For ABC trilayer graphene on boron nitride, it turns out that the Chern number is high. It's either plus minus 2 or plus minus 3, depending on parameters. And furthermore, there's only this can be controlled, whether it's this or whether you get a topologically trivial band, can be controlled electrically by changing the sign of a perpendicular displacement field that the experimentalist can apply with a dual gate. In twisted bilayer aligned HBN, where you open up a gap between valence and conduction bands. The Chern number is plus minus 1, and twisted double bilayer graphene, the Chern number is plus minus 2, and so on. Right? So these systems are wonderful. They have flat bands, which are topological, and they're partially filled, and experimentalists can tune the density. So we have a great chance to study strong correlations in a partially filled topological band. Okay. So what can we say about the strong correlation problem? Right? Again, I'm going to keep the focus very tightly on correlated insulators at the special filling of Ward 3 of these moire bands. There's a lot more that's going on in experiments and in theory that I could talk about, but for the purpose of this talk, I'll just focus on this. Right? And this filling includes both spin and valley, so it's really a quarter filling of the bands, or 3/4 filling. Now, the first thing you can try to do, and there's a series of papers doing this, and I think Chun-Li Wong talked about his most recent calculations, is to just do Hartley-Fock in the flat band limit. And in Hartley-Fock, what you find is spin and valley both polarized, and you get spin valley ferromagnetic order, and you completely fill a band. That's say filling nu t equals 1. Right? So you start off with 1 band per spin in each of the 2 valleys. This band for valley K, you have Chern number C. For valley K prime, you have Chern number minus C. And you turn on interactions within Hartley-Fock. If your filling is 1, you just fill 1 band out of these 4. Right? And since just filling 1 band, you'll naturally get a anomalous Hall effect with Chern number C. Okay? So that's the Hartley-Fock story. Now, so this is an interesting result because the strong coupling ground state is a strong ferromagnet with the scale of the magnetism set by the Coulomb interaction. And this should be contrasted with conventional magnetism in a non-topological band where you have antiferromagnetism, which is scale set by T squared over U. Right? This is an order U phenomenon. Right? So that's great, but you can worry, is Hartley-Fock reliable? Well, Hartley-Fock is historically known to overestimate ferromagnetism in all kinds of solids, so maybe we're just deluding ourselves. So we can try to confirm this expectation with some numerical calculations and some analytic arguments. So we did some exact diagonalization on small system sizes for, again, a variety of these plus minus C Chern bands with parameters chosen to match these diverse systems. And in the exact diagonalization, we always saw that in the strong coupling limit, the ground state was indeed a spin and valley polarized ferromagnet. Right? So that gives us some confidence that Hartley-Fock is getting things right in the strong coupling limit. Now, there's also an analytic argument that one can make, which is actually quite powerful. It works only in the exact flat band limit where there's no kinetic energy. So if there's no kinetic energy, what's left of the Hamiltonian, right? It's the interactions and the band topology, right? So you isolated these 2 elements from the 3 elements that define this problem. So the Hamiltonian is just a density-density interaction, and the band topology lurks in the expression of the density in terms of the electron operators. There's a form factor, and it's this form factor that knows about the block functions and therefore about the band topology. Okay, so this Hamiltonian, it turns out, is positive semi-definite, and the spin valley polarized ferromagnetic state is annihilated by this Hamiltonian. It's 0 energy eigenstate, and therefore it's a ground state. Right? So that's some analytic support for the statement that in the strong coupling limit, you will get the same answer as in Hartley-Fock. So the conclusion from all of this is that you get a ferromagnetic insulator in these plus minus C Chern bands at odd integer fillings of these flat bands. Okay, and there'll be an anomalous Hall effect, a quantized anomalous Hall effect of CE squared over H. So this is actually seen in a variety of experiments. So shortly after we started writing papers on this, Goldhaber-Gordon's group studied twisted bilayer aligned with HBN, and followed by Andrea Young's group. I'll show some of the data. And also data on ABC, there should be tri-layer graphene, autocorrect, sorry. on HBN at nu t equals 1 sees Chern number 2 quantum anomalous Hall effect. And as far as I'm aware, I think this is the first experimental observation of a higher Chern number quantum anomalous Hall effect. So here's data on TBLG aligned with HBN. So this is the data from Goldhaber-Gordon, where in the Hall channel, he saw hysteretic transport below a temperature. The rho xi is big. The Hall angle is big, but the rho xy is not really quantized, was not really quantized in his first experiment. A few months later, this was followed up by Andrea Young with a different device. But again, TBLG aligned with HBN. 5 minutes? Okay, good, thanks. And once again, and here there's a very beautiful quantization of the Hall effect. It's quantized to 3 orders of magnitude. And it sets in at high temperature. You see this below about 3 Kelvin. And if you remember that in Moire, all energy scales are low. 3 Kelvin is a high temperature quantum anomalous Hall effect. You know, Dan Dessau was talking about 1 Kelvin in MnTi2, whatever, manganese bismuth telluride, in a system where energy scales are much higher, right? Now this, from that point of view, this super high quantum anomalous Hall effect. And this data on ABC trilayer graphene on HBN, you tune the displacement field, which, so this is the top gate voltage, bottom gate voltage, you tune the displacement field to be along here in this region. And then you measure the Hall effect and you see a nice quantization above about 400 millitesla, and it's quantized to 12 kilo ohms, which is h over 2e squared, right? So Chern number 2 quantum anomalous Hall effect. So the real question is, should we declare victory, right? And I don't think so. I think things are looking good, but you know, it's always good to be careful before declaring victory. So the simple-minded theory that sort of dominates the theoretical discussion in the field has features that are actually not tested in existing experiments. And the theory assumes complete spin and valley polarization. Now, there's a lot of good evidence for valley polarization. After all, we see hysteretic transport. And the hysteresis, you know, the valley polarization is Ising-like, and it would naturally lead to hysteresis. But spin is an SU2 degree of freedom in these systems. Spin orbit is weak. So you don't expect hysteresis due to spin polarization. I claim that I think a lot of experimentalists make, but very few theorists seem to be aware of, is that we don't really know what the spin is doing from experiments. And this is emphasized further by a recent paper from Andrea Young's group, where he directly tried to image the magnetism in this TBLG aligned with HBN. And the measured magnetization, you know, it's a nanosquid measurement that he uses, this large uncertainties. But the measured magnetization per unit cell is about 2 to 4 mu b per unit cell. It's much bigger than the maximum spin contribution that you can have if you had spin polarization, which is 1 mu b per unit cell. And theoretically, you can estimate the maximum orbital magnetization, and it's also about 2 to 4 mu b per unit cell. So it's safe to say that there is orbital magnetization, but it's not safe to say there's spin magnetization. And there's other indications from experiments from Goldhaber-Gordon that also suggest the same thing. So what can you say from microscopic theory, right? The experiments are not actually in the strong coupling limit, which is where we have good confidence that you'll have spin and valley polarization, right? But they're at intermediate coupling. Now, once the kinetic energy increases, the bandwidth increases, spin ferromagnetism is expected to become less competitive because it does very poorly on kinetic energy. You know, this is the classic reason why ferromagnetism is often never seen, right? So standard Hartree-Fock is not going to help us answer what might go on, right? So we need to solve the problem of the possible spin physics in a correlated Chern insulator with some of the techniques, some of the theoretical techniques. So that's the real problem that that the title of my talk was about, the nature of quantum magnetism in a half Chern band. So it turns out that you can describe a number of different quantum anomalous Hall orbital ferromagnets which do not have spin ferromagnetism. And there's a theoretical framework for doing that, which is the partron description, what used to be called auxiliary boson. I think Sarah mentioned it in her talk. So you write the electron as a product of a fermion and a boson, then you put the fermion in the filled Chern band, and various things that the boson, this boson can be thought of as a Schwinger boson that people who work on magnetism may know about. And what this boson does, different things that the boson does gives you access to different magnetic quantum anomalous Hall faces. A simple example is a quantum Hall antiferromagnet where the boson condenses at finite momentum. So the spin could be an antiferromagnet, right? We don't know from experiments whether it's an antiferromagnet or a ferromagnet. Even more exotically, the spin could also, the bosons could pair condense, and this state would actually be a quantum spin liquid that's existing simultaneously with a quantum Hall insulator, right? People were talking about hot topics in condensed matter physics. I think this unifies, a lot of the buzzwords in condensed matter physics into the same state. Right? So clearly we need experiments to decide what the spin degree of freedom is doing. I'm almost done, so let me just flash one slide. I don't know, I'm out of time, right? So we can try to ask, it's good that the integer quantum anomalous Hall effect is seen, but what's interesting to do next, right? We can ask the possibility of a fractional quantum anomalous Hall state. Now, there's some very encouraging results from both experiments and theory that speak to this. So particularly in Andrea Young's experiments for TBLG aligned with HBN, the valley polarization, which he can detect from the hysteretic transport in RXY or RXX, that survives from 3/4 filling of the conduction band all the way up to 90% filling of the conduction band. So you stay within this filling range where you know this valley polarization. So then if there's complete valley polarization, you're in a situation where you're in a single Chern band that's partially filled, right, with spin as an active degree of freedom. And so we tried to do exact diagonalization calculations to address whether if you say fill 1/3, remove 1/3 holes from the fully filled band, we can get a Laughlin-like state, fractional quantum Hall state. And indeed, in exact diagonalization, we see that at a filling of 0.83 of the conduction band, we get a fractional quantum Hall state, a fractional quantum anomalous Hall state, with a gap that's reasonable. And as far as we can tell, it's a gap of maybe about 2 Kelvin or something like that. So I think this is something that experiments can potentially try to go after, and maybe they will, see something interesting. Anyway, so let me just stop here. So I guess the main summary point to emphasize is that these moire materials are an extremely powerful platform to study the interplay of strong correlations in topology and kinetic energy. The main success so far in this subtopic has been the realization of tunable quantum anomalous Hall effects, the integer quantum anomalous Hall effects up to high temperature. And there's some field-induced fractional Chern insulators. Again, very encouraging recent experiments from Emil Jacobi's group, interested by graphene. But no, I hope that this is just the tip of the iceberg. And just for Chimyao's sake, I put in this last sentence just to get his blood boiling.
Thank you, Senthil.
Hi, Senthil, nice talk. So when you talked about the fractional quantum Hall effect from partially filled Chern bands, those are specific to very certain fillings, right? So you have 1/3 filling and so on and so forth. But even in the Landau level problem, have competition between density wave orders and, for example, charge density waves and fractional quantum Hall.
Right.
Now, the question for you is, do you expect that the charge density wave orders that I presume you would get if you also go away from the 1/3 filling, would they be any different from the charge density waves that you would obtain from topologically trivial bands?
Oh, yeah, presumably. But first of all, I should say that even at 1/3 filling, even as filling 5/6, right? I forgot to put in the reference, but There is an exact diagonalization, very recent exact diagonalization work by Andreas Lockley that does find evidence, in some region of parameter space, you get the fractional quantum anomalous Hall state, and others, you get a charge density wave. Right? So you don't have to dope away from 1/3 filling. Now, everything's got to be different. You can't simply just localize the charge and forget about the band topology. Right? It's got to show up. You ask about it in what physical property or what experiment it shows up. So I'm not sure, but we can. I'm confident that it's got to show up. Yeah.
Hi. Can the spin ferromagnetism be studied by applying an in-plane field, or has anyone done that?
So Goldhaber-Gordon, his experiments do apply an in-plane field. And there's something very interesting that he sees, at least for the in-plane field, is as you tilt the field, the size of the hysteresis loop only depends on the component of the field perpendicular to the plane, which again clearly speaks to orbital magnetism as driving the hysteresis. Right? Now, it's a bit subtle to work out exactly what the in-plane field is doing in these systems. Now, naively, you would think the in-plane field only couples to the spin. But because the moire unit cell is so big, there's also an orbital coupling of the in-plane field. And twisted bilayer graphene, you can estimate the size of the orbital coupling, and it's comparable to the spin-Zeeman coupling. So in-plane field effects are not as obvious. How to think about in-plane field, it's not just Zeeman, right? So you have to worry about orbital coupling of the in-plane field. Now it shifts the momentum of one layer led up to the other and through the orbital coupling, and that it's an order one effect.
Thank you for a very nice talk, Senthil. Two questions. One, just quick clarification. When you say 5-6, I just wanted to understand, you're talking about fractionally occupying the mucal 1 band. You're inducing 1/6 hold into mucal 1 state?
Yeah, that's right. So in terms of the original conduction band, it's filling 5/6.
Oh, it's the region. You're talking about the full band, all 4 valiant and polarized bands?
That's right. Yeah.
Oh, I see.
Not polarized. In terms of the microscopic band structure, it's in terms of how many electrons you have per moire unit cell, it's 5/6
Okay,
times
that
4.
clarifies it. Okay. Yeah, I just want to make sure that, yeah.
And yeah.
The second question is about the state of the experiment. You alluded to it, but I was a bit confused. So on the next slide, you talk about not anomalous, but field-induced fractional quantum Hall.
Yeah.
Both from Amir Yacobi and from Andrea Young. I haven't seen the data. Could you say a few words about what do they see?
Oh, so there's an old experiment. So this predates the Moire revolution. I mean, I don't know the Moire revolution, but it predates the magic angle revolution. So this was in 30 Tesla field. Andrea Young's group found all kinds of fractional Chern insulators, then bilayer graphene on HBN, no twisting, right? So it's field induced, but it's a field induced quantum Hall state where crystal symmetries play a role, right? There's all kinds of details that you can work out that are specific to it being in a crystal, right? Now this more recent experiment is on twisted bilayer graphene in the in sort of the same doping range that I've been talking about, but now in the valence band, I think. And so what Yacobi's experiment shows is that you need about a 5 Tesla field to push the system into a fractional Chern insulator. Right? Now, if you extrapolate the data from above 5 Tesla back to 0 field, it occurs at some non-zero density per unit cell. Right? Now, the 5 Tesla field is a small field. The amount of flux you have per unit cell is 1/6 the flux quantum or something. So it's a small field, but not terribly small, right? And there's some reason, there's some theoretical reason why in that system that they were studying, it's natural to expect that you need that kind of field to kick you inside. But it's going in the right direction, right? I think, we've gone from 30 Tesla fields in a system where you don't expect anything at 0 field to something where there's a chance of fractional quantum anomalous Hall effect, but In the particular system studied, you needed this 5 Tesla to kick out other competitors. We'll see where it goes. The field is evolving very, very rapidly in terms of experiments. Right?
So, yeah, please.
Okay, I have just a general question, very general question. So graphite, if you do integration, you can get beautiful superconductivity and transition temperature is very high and so on and so forth.
Sorry,
Now-
where?
Graphite, if you do integration, you can get very high superconductivity, you know. So the general question I have is by integration into, let's say, graphite, can you also get some kind of band flattening and also some kind of magnetism?
Have no idea.
At least theoretically, I mean, integration people did a lot, you know, 80,
Yeah.
right? But at least theoretically, something.
Yeah, it's a good question to think about. There's a lot of theorists in the room. I have no idea what the answer would be.
Hi, yeah, great talk. So I have so I'm curious about this 5/6
Mhm.
fraction you find. Is this you find it the only fraction you find? Is it of electron on whole side?
No, so the we only looked at one side. We looked in the conduction band. I don't know, I'm going the wrong direction. You know, the place we looked is the place where Andrea his experiments told us there was valley polarization. Right now, you know, to limit the size of the calculations, if we assume valley polarization, we just have to think about one Chern band, and it's easier to have a more reliable theoretical answer. Now, if you go from 3/4, if you decrease the filling towards neutrality, then Andrea does not see valley polarization over a wide range of fillings. It's only in the site away from neutrality, as your electron dope from 3/4, that does this wide range of hysteresis, where there's hysteretic transport. But in that range, we also looked at another filling. I forget now, it was 12. It was close to 0.91, it's like 0.89. There's some rational fraction that I'm forgetting. That also we found was a fractional Chern insulator, but the gap is smaller. Right? And anyway, close to the edge of where valley polarization was observed in this device. But as you know, each device in this field is its own universe, and there's various structures. You know, monolayer, bilayer graphene is actually very interesting for the purposes of seeking this FQH. There's a couple of experiments, maybe 3 experiments so far. But we'll see. You know, 6 months later, the story may be completely different.
Oh, yeah, thank you. So I was just also wondering if there's any, do you have simple physical picture to explain why this particular fraction or some, yeah.
Oh, yeah. So this, you know, looks like 5/6, some weird number, right? Wherever it went. Yeah. But it's not that weird, because what we are doing, I think Bandri was asking you, the valley polarization means that you filled one Chern band, but you don't know anything about the spin, right? Now, from this filled Chern band, you're adding electrons, meaning in the whole picture, you're taking a whole band, which is filled one Chern band, and then you're removing holes. And the amount of holes you remove to reach 5/6 is exactly 1/3. Now, in the Landau level, 1/3 filling is very special, right? It's the most prominent quantum hole. So that's the reason to look at this. Yeah, so that's the intuition.
Senthil, maybe I can ask a technical question very quickly.
Yeah.
So this Parton
Yeah.
procedure that you alluded to, presumably you're doing it in real space.
Yeah.
And so is there something?
Yeah, there is
particular?
something. So that's what we first did in this paper. So we finished the issue of working in real space by not, you know, by simply asserting that F is in a filled Chern band, right? That's finishing. It's not, we're not really being faithful to the microscopes of the system, but we have figured out how to do it in a completely legitimate way, microscopically. And explaining that is an entire separate talk. That's not, I'll be happy to tell you in
Thank you.
private.
Maybe very quickly.
Yes, and next page, you were saying, talking about magnetization of the field. So this is squidness, right?
Yeah.
How?
Nanosquid.
I know, nanosquid. How would you tolerate nanosquid with the field?
As far as I understand, Andrea measures what he ends up measuring is the gradient of the magnetic field.
But still, you put a field that kills it, right?
No, so there's a field, and then if there's a field gradient, he's able to pull out.
Oh, I see. So not real field, but typical field.
No, it's a nanosquid on tip. So everything with the compound is buttered on the tip of the pebble.
Oh, nice. That's great. Yeah. Also, I'm curious, right? What's the progress?
Great to have experimentalists in the room who actually understand experiments.
No. What's progress now detecting the Meissner effect?
The Meissner effect?
With this new tool. Sounds so promising, so exciting. Thanks.
Yeah, I'm not aware of any attempt to detect the Meissner effect, but I know that Pablo worked with Eli Zeldorf at Weizmann, and they imaged the twist angle disorder, the variation of twist angle across twisted bilayer graphene magic angle device. And you see that it's flat, and then there's discrete domain walls where the twist angle jumps. So that's the only other measurement using nanosquid that I know of. I guess no moire experiment. I guess Genie only moire experiments. Are you aware of other nanosquid? Yeah, I think there's only two, as far as I understand, only two labs in the world that can do nanosquid, Zeldorf and Andrea. Yeah. Again, these techniques as they develop, hopefully all kinds of other things will be learned.
Sounds like a very good lunchtime discussion topic. On that note, let's thank Senthil and